see it. It's not the right one. Here we go. Okay. I did. Late for office hours, but on time for class. That's all we can hope for in life. So.
Hello.
Back. Good after the noon. It's like less apocalypse outside, but I'm gonna cancel the observatory thing. Ever seen it?
Yeah.
It's so the big old coyote. Oh, I see. You saw that. I know they tried to get me to get donuts, and I was like, I want them, but I have my hands full. Sorry about it.
Let's make a second trip.
Yeah. You can go get one. You have to go get one for me. If you get one for you, you get one. Yeah, that's the rule. You know what the rules are? You show up late to class, you have to show up out of breath, or with snacks.
Oh.
That's the only ways you get to show up. I will wait for Dante to come back and then we'll get it cracking. All right. That's the class, right? Oh. David, I saw him earlier. Blue shirt, you know. Yeah. Is that what it is? But you don't believe. On record. How's homework looking? You started it. You started it?
I squad glimpsed over.
You started it?
Yep.
You started it? Oh, okay. Look at it. Talk to the people who started it.
Close enough. I like it.
Oh, fuck, I crap. But you don't need those ones for the last one.
For 5? Yeah. Sorry, no.
Oh, maybe you do. For that moment of inertia.
Well,
It's everything that we did on the board.
start with the contemporary.
Yeah. Yeah, it's not different math. The only thing you're going to change is the row, right? So imagine a different density distribution. Now we kind of talked about how that would work, right? You just have limits of integration, radius, and I don't think there's like a azimuthal component in that problem. Okay, so we were talking about the moon. We're going to finish up our discussion of the moon, and really we're going to start thinking about these things. Like you've taken the intro astro class, so you've seen that there is a moon. That's sufficient, right? Now we're going to talk about what does spacecraft data reveal about the moon, and then how does that contrast with Mercury? So as you'll see, Mercury and the moon share a lot of properties, and of course they're different in a lot of ways. And what does that tell us about the origin of the moon? What does that tell us about the origin of Mercury and the history of both of these bodies, right? Those are the things that we're interested in, because we're using both of these airless bodies as laboratories for understanding sort of the terrestrial planets that don't have atmospheres. Okay, these are ancient records because nothing has been eroded, right? Okay, so we'll talk about some physical aspects. We'll talk about the temperature, and it'll be a really brief conversation about the temperature. We'll just sort of introduce how we do that. And then we'll compare our predicted temperature to what we see. And what that'll tell us is whether or not there's any internal heating. Because if the surface is hotter than you would just get from the sunlight, then of course there must be something coming from below, right? There's no atmosphere to warm it. There's no greenhouse effect. And finally, we'll talk a little bit about the composition that makes the moon very similar to Earth, and what are the ways that it's the same. Okay. So let's go back through those. We went through the moon pictures very quickly. Let's move more slowly right now. Uh, oh my god. Alright. That's the moon. Anyone know what anything is called? Any of the places you see?
No, there's Tycho crater.
Tycho, yeah, so that's the easiest one. This is Tycho. Biggest one, most memorable, right? You only have to remember one crater to get that one. Tycho. Tycho crater. Okay. Any of the seas? Mare, yeah, so they're called Mare, but do you know the names of them? Okay, let's just learn. I think that's what the next slide is. Come on. Okay, so there's a Maria. We don't care about that. Highlands, of course, have a different color. We talked about that a little bit already. We also talked about the fact that they're different ages because of radiometric dating. Here's the rest of them. Come on now. Oh my god. All right, that's fine. We saw how it goes. So there's Tycho. Some of your other big ones. Here's Plato. Over here you have Aristotle and Thucydides. I don't know. But the ones that you care about are like Mare Imbrium, Mare Tranquillitatis, and then this one here is Oceanus Priscillium. And so the thing to remember about why these are all named this way is we're looking with 1500, telescopes from the 1500s. And first person looking is Galileo, right? And Galileo's looking up at these objects and he sees craters and he sees mountains and he sees these large flat plains. They look very flat, no mountains on them. And he assumes that they are seas and oceans, dark seas and oceans. So Mare means sea, Oceanus means oceans. Now he's wrong, but he doesn't know that, right? Okay. There's the landing sites. They're different. So this one's landing right on the edge of the sea because they wanted to be able to grab some of that Mare versus like some of the early ones. Here's Apollo 11 right here, grabbing. That's where we first landed on the moon. Grabs this stuff. Cool. Maybe I should throw more moon images in there. Okay, there's the far side. And this is the weird one that you won't memorize because you'll never see it this frequently ever in your life ever again, unless you work, for example, on moon data. So it's almost all highlands. It's very different from the near side. Of course, there are a few of these like sea-looking things that are filled in, but here you have that direct connection. For example, this object right here looks very dark inside. And that's because, as we talked about before, you punch into the crust and then the crater itself fills up with basaltic lava, right? Okay. Come on. There we go. Okay, here's the North Pole. Ever seen the North Pole of the moon? Not yet. And so what you're looking at here, there's no cap, obviously. There's no volatiles that are as abundant as there are on Earth. We'll talk about why that is. But there are certainly places of pretty close to permanent shadow. And we'll talk about why that is important if you want to think about, say, going. And then, hold on. So, what did I do here? This is two different images. Okay, this one is the whole. This is the whole object there. It has the view from the north. Okay, you can explore the moon on your own. It's pretty fun. You can go on Google Earth and you can drive around, and you can do Google Earth on the moon. And it has images from the surface. You can like explore all these craters if you like that. You can also do it on Google Mars too. Pretty fun. Okay. Fine. I guess my clicker not clicking today. All right. So let's really just talk about some of the main geomorphological features that we're going to see. So you've already seen the Mare or the Maria, sorry. And this dominates on the near side, right? So this is like very dark rock. We talked about what the composition was already, and this is due to huge impact craters, right? You have these things called rills. They're mostly in the Maria and the crater bottoms, so they're straight rifts. We'll talk about how they form when we see similar objects on Mercury, but hint it's a cooling feature. Scarps, they're mostly in between craters. These are huge cliffs. They're shallow and scalloped, as opposed to the crater edges, which tend to be sharp. Right, they're just like this, and they fall. And this is in contrast to say the highlands. The highlands are your much older rocks, right? That's your probably original crust. It's obviously been cratered as well, but it's less cratered. Sorry, it's more cratered than the less cratered Maria. And then there is some canyons, and these are surface features that come from seismic fracturing as opposed to erosional features. So canyons on Mars, sorry, canyons on the Earth, for example, the Grand Canyon forms because of a river, right? And that river has been flowing for ages. And so it keeps digging. There's no rivers on the moon. So all the canyons that you see on the moon have to form through seismic features, right? Similarly, when we see Mars, we'll see that there is the largest canyon system in the solar system, and that is not formed from erosion. That's formed from cooling, right? You basically think about that as you pull something very hot out, and then it rapidly cools, and the surface shrinks and cracks, right? We talked about craters. That's mostly what we talked about at the end of class on Thursday. And of course, there are some fun, prominent features about craters. One, they have rays, right? And that's that material that gets exhumed and then explodes and lands back on the surface. And typically, it's a different color, right? So you have weathering processes on the surface, and then new material sometimes is much lighter, hasn't been weathered, and so it's brought up to the surface, and just like you saw at Tycho, that's what gives it a beautiful, bright white color, right? These ejecta rays. Sometimes you see crater chains. So on the Earth, you'll never see crater chains as well as you'll see them on the moon, because of course they get eroded. But on the moon, you have this great thing that happens when you have multiple objects hit at once. And so you can have, for example, one thing hit. It's really hard to tell, of course, whether it was one body that hit and then sent something else to hit later, or whether the object itself, for example, if it were a comet, we often know that as comets get close to bodies, they can become elongated and break up. And so, for example, when we look at a comet impact on Jupiter, you'll see that the Shoemaker 11.9 comet impact wasn't just one, right? The comet came in, but it was distorted and then smashed into multiple places. Okay. There's no volcanoes. There's no volcanic craters on all of the moon. Okay? There's no atmosphere. And I say this with quotations because the idea of an atmosphere not quite inappropriate here, but there is gases that escape from the rocks. There's gases trapped in the rocks, and then they make their way through. But the gravity is so small, and as soon as a particle of gas makes it to the surface, it now has enough energy to escape. So typically, when we think about an atmosphere, you would call the boundary at which particles have enough velocity to leave, you call it the exosphere. And it's a section of an atmosphere, it's the top part of the atmosphere. But essentially, the exosphere touches the surface of the moon. Okay. All right. Moon's weird. So the moon's rotation and the revolution and rotation periods are the same. So that means that it always shows the same phase to you. Because as it goes all the way around in a 28-day cycle, it also rotates once. Right? So this is called tidal lock. Yeah.
Is that why we always see the same face?
Yeah.
On here?
Yeah. So that's called tidal locking. You can call it synchronous rotation. Either one is fine. Synchronous just means happening at the same time. Right? So the rotation and the revolution are the same. And this tidal lock-in is due to conversion of the moon's rotational energy. Okay, a process driven by tides in the interior. So we all know, hopefully we know, that the tides on Earth are caused by the moon. You have 2 tides per day, and the tidal bulge points at the moon. And then there's one on the other side that points away from you. And I hope you remember why that is in your 2300 class. So that tidal lock-in, that fluid, that bulge moving around, is dissipating energy. And particularly, it's dissipating rotational energy. So for example, when we look at the surface of the moon, we see one side is very different than the other. And it turns out that these are related phenomena. Okay. This is a fun word. Anyone know how to pronounce this blue one here? What?
That's all.
Yeah, so you think it's French, right? Maybe. It's mass cons. And it stands for mass concentration. But, you know, if you look at it, and you're like, oh, is this some like, you know, fancy terminology from ages past? No, they just shortened mass concentration. So what you're looking at here is you can fly really close to the surface of the moon. Okay, take your spacecraft and going around in orbit. And you have an expectation, if it were a perfect sphere, that it would go in a perfect circle, right? But let's say there's a bulge. Let's say there's an area where there's more mass. As you fly over that area, what happens?
Gravity.
Yeah, gravity great, right? So you get pulled, you start moving faster, and then as you move past it, you start slowing down. And as we fly around the moon, you can measure deviations from a perfect spherical orbit. You start speeding up and slowing down, speeding up and slowing down. And those are areas of mass concentration, right? There are also moment of inertia anomalies because, of course, there is rotation. We don't really think of it as very fast rotation. It's 28-day rotation, right? And interestingly enough, look at this. The center of mass of the moon is 3 kilometers closer to the Earth than if it were a sphere. I'll say that again. Take a sphere, okay? Think about all the mass being distributed inside of it. Think about spinning it on its axis. Okay? The center of mass you would expect to be on that axis. It's not. It's shifted towards the Earth side, the near side, obviously, to us, right? So it's got to be a really weird mass distribution inside because of this pulling, right? So because it's been under this tidal effect, this feeling of differential gravity from the Earth, that is to say, the near side of the moon versus the far side of the moon, they experience 2 different amounts of gravity. The near side is being pulled harder, the far side is being pulled less hard. So as the thing cools, you have a pull towards the Earth. Now, of course, you're still within this giant sphere, but you have mass that's moved towards the Earth. Make sense? Okay. It's got this thing called soil. I put that in quotations because if you just talk to anyone who actually cares about soil, they'll say that that's a lie. What do you need in order to have soil, according to people who care?
Don't look at me, I'm not one of those people that care.
Okay, you need bacteria. Yeah. So yeah, in order for it to be considered soil, it needs to either have bacteria in it or have had bacteria. Yeah. So I put it in quotations here because we have no evidence, of course, that there was ever anything living on it.
Soil.
No, it's just bacteria.
Yeah, but like,
I don't think they knew. I think that version comes before we realized that bacteria exists. Because that's a very old definition, right? Like if you soiled your clothing, that's like medieval times.
but then it's dirty. Bacteria.
Yeah, that's true too.
That's why.
It works both ways. Yeah. Okay. So we're gonna call it something different. We call it the regolith. And for airless bodies in particular, you know, this idea of regolith is really important because you might have, say, an asteroid. You might have something that is not spherical. It has enough gravity that it's like, not just a rubble pile, it's rocks all together, but you can potentially stand on the surface. But what you'll be standing on is potentially inches to feet of sort of soft, low density material. And it's usually very fine grained. So the way that a lot of it is created is that you smash into the object, you break up the rocks. And then you smash into it with really, really small objects, and you break up the small rocks into smaller rocks. And it's called micrometeorite gardening. One of the only ways to erase anything on the surface of the moon is to wait long enough that dust sort of moves around. And remember, it's not moving because of wind, it's moving because it can get electrically charged, it can lift in the solar wind, and then it moves until it finds a free electron, or it finds a free ion and becomes unelectrically charged. Okay. Questions about that? Okay, we're cruising through the moon right now. Oh no. Here's the interior structure. And this is different from the composition. We're going to look at this in two different ways, and we'll try and do this with all of the bodies. So we'll have two different types of definitions for each of the sections. Okay. How do we find out about the interior? Well, we put seismometers on it. How did we put seismometers on? We went there, right? We saw all those places. And so if this is the near side, right? We put one over here, we put one over here, right? And they're not big things. They're just vibration detectors, and they detect vibrations in three directions, right? So essentially you have something that does this, like, oh shit, then they send that information to us, right? So you can find the propagation speed of seismic waves, and that really depends on the mass density. How is mass distributed, right? So if, for example, you have one seismometer here, and one over here, and one over here, then you can watch for propagations throughout the interior. Now, I told you at the beginning there's no volcanoes. So do you suspect that there are moonquakes? Yes? Yes. Okay. Is that it? Just one answer? Everyone likes Garrett's answer? Do we think that's the most common way of probing the interior? What else can we use? Moonquakes would work too, but what else? What's all over the surface?
Craters.
Impacts. So because there's no atmosphere stopping small bodies from making it to the surface, it gets impacted a lot. So you can use both moonquakes and impact craters, right? And so you can see that happen. Because if I smack the surface over here, it sends surface waves through the crust, and then it sends waves through the core. And of course, they arrive at different times. That tells us about the composition of the density. Okay, so we got some fun words. Lithosphere. What does litho mean?
Sounds like lithium.
Okay, yeah. Yeah. Those, it's not for that, but yeah. Okay, there's no F, but you're close. Lithosphere means rock sphere. Yeah, very I don't know where this one comes from. I don't have another word for it. A asthenosphere, so you can tell that this is the crust, right? That's the top part. The asthenosphere is the mantle, and the core is the core. And they'll call it like the core sphere, which I think is some stuff or two. The lithosphere is thick, about 50 kilometers thick. The mantle is the rest of it, and then the core is big. It's 340 kilometers. It's probably partially melted nickel and iron. Like we think, for example, that the moon was well differentiated, even if the core may not be exactly what we think it should be. Now, of course, if the core is 3 kilometers towards the Earth and the whole core radius is 340, then that is about a 1% deviation, right? So that puts it into context a little better, right? And here's the rocks. Here are the rocks. Here's the rocks, in the lithosphere, 3 grams. So what is that? Three grams per cubic centimeter? Rock, good, okay. Now we know what kind of rocks. These are feldspars and pyroxenes. Inside is about 3.3 olivines and pyroxenes. And 7.2 in the center, of course, I said was the nickel iron mixture. Right? So this is how we can tell, just based on the density and the density distributions, what the interiors are. Right? Because think about the farthest we've ever drilled on the earth. Okay. Like not more than 100 miles. Right? You can't, right? This crust was, what did I say? 50 kilometers? You're not getting into the core. You're not getting the core anyway. So the only tool that we have are mass concentration, moment of inertia, right? This is telling you what the crust is made of and how thick it is, right? That's the crazy part. We can say, oh, because of the timing variations in seismology, I know that the crust is approximately this thing. And there's the boundary at which waves bounce, right? Because anytime you have a density change, you have waves bounce off of it, right? You remember that from, you know. All right, that's the moon. Any questions about the moon? Here's the types. Okay. On the left hand side, you have the minerals. Okay. Just because we don't remember this very well, you have highland rocks, which are very different from your basaltic rocks. Remember we saw this picture of the anorthosite here, and then it had the picture of the one on Earth with the sign above it. Yeah, this exact picture, right? And it's very light comparatively. Of course, in this picture, I think this is a black and white picture, so it's not very helpful. This one is in color, but these are much darker. And you see this type of like this porousness that exists in the basalt. You see this in volcanic rock a lot as well. If you like go to Hawaii. And of course, the color here is very, very dark. We saw that the albedo for the moon was about 12%. That's darker than most rocks. Okay? So this is a small component of the total. I don't know how much I want to talk about what the minerals tell us here, but I'll give you the if I can do this well enough. I'll give you the shorthand. Okay. These are the same rocks that we have on Earth. Right? Many of them the same types of rocks that we have on Earth. There is a major difference than the rocks that we have on Earth. And that is a lot of these rocks lack volatiles. What does that tell us about the interior? Okay. If the interior lacks volatiles, then whatever formed the moon cannot have had a high amount of water. Now that's very unusual, right? Because if they form from the same rocks that we form from, we do have a lot of hydrated minerals. And we have them in the interior of the planet, right? We have them on the exterior of the planet, obviously, and we have water, right? So the biggest question is, what happened to the volatiles? What happened to the water that were in the moon rocks? And likely the solution to this, I think we may talk about this, we may not, is that during the impact event, okay, you probably started out with very hydrated minerals, but it got so hot and it was a low gravity environment that those hydrated minerals or the water in those hydrated minerals simply. Right? And that's how you can look at sort of a cataclysmic forming, as opposed to what was the prevalent or one of the versions of the theory at the time was that they formed with one another, right? Because if you form very slowly, then those hydrated minerals can sort of seep through and make it to the surface and contribute to the water content or the volatile content. But if it happens fast, then they're destroyed, right? And they're not retained in that process. So if these two things were friends, formed nearby, sort of formed around each other, one got captured by the other, no big deal. But if they hit each other and one was destroyed, then that would be very big, right? Okay. And that's what you can tell from rocks. Right? Geologists can tell you that. Not me. Okay. So most of the craters are very old, right? And we talked about that in detail. You're gonna see much more of this in homework 2. I'm gonna give you pictures of the moon. And you're gonna count craters. I don't want to do that. It sounds shitty.
Do it again.
It's fun, okay? You'll love it, maybe. I don't know. So and it's teamwork too. So you'll do it together. Yeah. Okay. So as you smash into the surface, you can't get replenished. So you run out of things to smash into the surface. So at the very beginning, there's a lot of things. And now there are fewer things. Right? That's the process of adding stuff up. Okay. So we can do radioactive updating. We talked about that in detail. And you're working on that in that homework. And what that allows us to do is to pin direct ages to the rocks that we find at a certain location. And then you have this crater count. So you have one version that tells you about relative ages for the entire planet. So if I look, say, at the density of craters that are larger than 2 kilometers in this area, and I compare them to the density of craters that are in this area, then I know that the one that has more craters must be older. So now I have a relative age between the two, right? And now if I only go to one of these sites and I land here and I grab a rock and I get the true age, now I also get the true age of that because I already had their relative ages, right? So that's how we're able to age date the moon so well. Okay. I did that. Wow, good words, Sam. Here's the numbers, right? And here's how we land. Okay, and you have all these craters in here. That's a cursor, that's not. That's like a screenshot of the cursor, that's not a real thing, right? And so folks can go in and you can draw a little circle and you can count the craters. And of course, since you know how far away the object was, you know how big the image is, you can find a physical size of that. And so people have gone in, they've counted every single crater they can find. Right, so be grateful that you didn't do that in grad school. Someone did. Okay. You're gonna do this in homework too. This is gonna feel very real. Okay. So we talked about the fact that the Maria are relatively crater free, and you can see that here, right? So like, look at the difference just from here to here. Right? So this is Highlands, and this is Maria. And one of the features that you tend to notice, okay, I got some craters, I got like what looks like mountainous type things. How that formed, we're not gonna think about that. But what do you got in here? You got some nice roads, right? You got some nice like straight long lines. Some of it will bisect or go through some of the craters. Of course, that tells you which order they formed in. Because if you were a rill and then you got punched through, then you have a hole in the rill, versus if you had a rill afterwards, it would crack the crater. And where they're overlapping, like this one here is a small one on top of a big one. This is telling you about the chronology, which one comes first, right? So just in one picture, you can tell a lot. And so that's how modern science works. You grab one picture and then that's your whole paper, right? Okay. The Maria are relatively crater free. The places that are now melted largely resurface a large scale lava flow. So what that means is that maybe you had some really nice highlands, you punch into it, you weaken the crust, that lava bubbles through, not bubbles because there's not a lot of bubbles out, but it oozes through, right? Because it's very slow, very low viscosity, and it just flattens out that whole area. Okay. So the large scale lava flow resurfacing probably has to do with the synchronous rotation. Okay, it's a little unclear how those are linked. You may be thinking to yourself, and this is incorrect, so I want to just like put this out here so you're not thinking this. So you may be thinking, okay, this is the Earth, and this is the moon, and so therefore maybe more stuff hit it from this direction as opposed to this direction. There's no evidence to support that. Right? It's not as though there's a preferred direction because they're quite far away from each other. To do this to scale with the moon about this big and with the Earth about this big and the moon about this big, you would need to place one here and one here. So 25 feet. So they're not protecting one another from strokes. Does that make sense? So the reason why one of the sides has more Maria on it is sort of we think that it has to do with flexing. So for example, you're pulling the crust in one direction, and maybe when magma becomes what's it called? When it's no longer in its crystal state and it starts to become, I mean, it's not really a fluid, right? Because it's sort of moving under these high pressures, but as it does that, maybe it has a preference towards the earth. So you want to figure that out. Okay, let's talk about the temperature of the moon. Is there heat coming from interior moon? Yes, it's really quick. Is there heat coming from the inside of the moon? No. Yes? Okay, you don't like it? Alright, let's find out. There's a shadow of the moon. Is that my mouse? Like, is that always there? Hold on. Damn it. Alright, classic. Good thing no one watches these. Alright, so this is the shadow of the earth on. What up? Wait.
That's not our shadow.
This is the earth? No, this is the earth?
Yeah.
Oh, okay. What's this one?
Shadow.
Shadow. What's this thing?
I can. Those circle.
Yes, it's a circle. You look at when you get home. It's great.
Oh.
But it's like one of the few great
Earth square?
Yeah.
Oh, okay.
Alright, how can you tell it's the earth?
Yeah.
Because of blue. Big pale blue dot. Yeah. And this is the cool thing too. A lot of people ask this question, like, could you see the stars at night if we didn't have an atmosphere? And there's the answer. So if you imagine what it would be like to stand on the moon with no atmosphere, the sun would be over there, but you could look up and see the stars. You can't see this in any of the photos because cameras don't have the dynamic resolution, but your eyes do. So you stand on the surface of the moon, you look up, you see the Milky Way. Like the best conditions in the world.
Oh.
Well, we can't. Anyways, you go to the moon, just let me know. Have it. Okay, so suppose the moon is only heated by sunlight. So then it has to be, we did this calculation in the first week, determining the relative contributions from sunlight and from radiation in the interior. Remember that? So let's see what the perceived temperature should be if all of the light that it got from the sun was absorbed and then re-radiated. Should be able to determine what temperature it is, right? Okay, so we have this fun one. We have the flux, and that's just the luminosity of the sun divided by 4 pi r squared, where r squared is the distance of the moon from the sun. Now, does it matter, for example, that the moon is going around the earth like this?
Distance.
Yeah. No, it doesn't, because this is a small distance, and the distance to the sun is a big distance. It's less than 1%. Okay, and in this class that means 0. Okay, but the thing we do want to know is how big is the moon. So the moon, for example, creates a cross section. It's always a circular cross section, so it's pi r squared, and that's how much light it takes up. Okay, so now I can just use these two facts. There's the radius, by the way. I don't know if I remember to say that. And we can use these two facts and we can turn it into a power. The flux times the cross-sectional area is going to give you how much energy per unit time you get in. And then you can take that energy per unit time and you can compare that to what you would radiate as a black body. So that's this. This is the radiation as a black body, assuming that it's the same. So you say, okay, this is sigma t to the 4th. But this stuff, this is the size of the body. And so if you compare these two, you can get an expression for the temperature that you would expect from a body that was just receiving sunlight. You recall that last time we did this, we had something like this, but this had a term. So this would be equal to 1, so this would be the contribution from the sun plus a radiation term, right? We're going to drop the radiation term and see what we expect just for the temperature, right? So we have something like a perceived temperature of about 278 Kelvin. That's the calculation. Okay. We won't have to do this calculation exactly, but. And so now we can go measure. How do we measure the temperature on the moon? We stick a thermometer in it. What about it?
I'm just thinking about.
Right, so we need a spacecraft, right? And we're gonna use light. What kind of light? Infrared, right? So we use infrared cameras to determine how hot it is, and then we look at luminosity in the infrared, right? Okay, so let's have a look. 278, everyone believes that? Yeah. What? Yeah, I mean, that was a back of the envelope calculation, right? You can do that at home. So hold on. That's 278. Very simple, first order approximation, assuming that assuming that the moon is a circle, it's not, right? Of course, the moon has a shape, spherical. Now let's look. So here's the data, this is spacecraft data, not a simulation. And we can make a comparison, okay? You can see this is the daylit side of the moon, and this is the night side of the moon. This is the original data, and then the right is the temperature data. So of course, the hottest part of the moon is the part that's going to be directly pointing towards the sun. So just like the hottest part on the Earth, it's like near the equator. The sun's almost directly overhead, as opposed to when you get near the poles and the light's hitting you sort of edge on, so you get less photons per unit area. So we expect the poles to be colder and the equator to be hotter. That's sort of a standard way of thinking about heating. And so we look and we say, okay, the equator is about 380. That's way, way higher than our calculation. But the poles were at 120. That's way low. And the average? 74. That's pretty good. What do we choose? Damn, that's pretty good. Right? Okay, so is the interior heating the exterior? No. There's no evidence to support that there is significant heating from the interior. Right? Does that mean that the interior is cold? No. Just means that there probably isn't a lot of radioactivity that's going into distributing heat, like there is in the center of the Earth, right? So there is a significant amount of heat coming from the interior of our planet still, like we hot. Okay. Is that cool? Some way to check it, right? Okay, so we use infrared to determine temperatures, not only on bodies that have a surface, but of course we'll see this for Jupiter as well. We can measure cloud composition and temperature, right? So you get the composition from one instrument on the temperature from another, and then you can piece together the chemistry. Right? Simple? Okay. Let's talk about. Shit. Wait, didn't we do this? Oh God. Why is this here? Well, I guess this is supposed to come earlier. Anyway, that's rocks. Here's your definitions of rocks, if I didn't say it already. Oh, there we go. Moon's all igneous rocks. This is maybe the only line that I want to do. Igneous rocks, of course, come from the melt. And they're cooled slowly enough to form minerals. At least at the exterior, right? As opposed to sedimentary rocks. What's your favorite sedimentary rock? Do you know any sedimentary rocks? Yes, you do. Everyone knows a good sedimentary rock. What about sandstone? Ever heard of sandstone? No. You ever heard of limestone? Okay, what's limestone?
They use it like construction.
They use it for construction, good.
Water.
Yeah, so limestone is fun, right? So it forms, where does it form here?
It forms up the bottom of seeds.
Yeah, and guess what it's made of?
Lime.
Lime, you think it's lime, right? Yeah, no, it's not lime, there's no lime at the bottom of the sea. But you know what there is? Abundant? Life.
In
And
limestone?
No, hold on, in the ocean. And then shit dies, sort of life. And the corpses fall to the ground. And they get packed 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 and packed and they form rocks. No, right? Yeah, so there's like diatomaceous earth, which is like, you know what diatoms are? They're like this little forget how many cells, they're multicellular organisms, but they're small, baby boys. When they die, they form this really like carbon rich earth that people love to use. Like you go next time to the garden center and you look for diatomaceous earth, that's what you're buying. It's diatoms, diatom pods. They're not still in there. Yeah, they're dead. Okay, so sedimentary rocks, right, is deposited. And sedimentary rocks is where you find, for example, if you go to Colorado, remember we were talking about the fact that you have this sandstone, and then you have granite that came through and punched a hole, right? So when you have this sedimentary rock and you punch through it, because these layers form right on top of each other, if you then expose it and you look in that sedimentary rock, it has a record. It has a stratigraphy of everything that's happened since that rock formed, right, so to speak. And so that's where you're going to find your dinosaurs. That's where you're going to find different types of dinosaurs. So there's this place in Colorado called Morrison, where you start on one side of the sand wall and you see like animal tracks, like in what was an ancient stream. And then you walk into the mountains and you see different dinosaurs in history, frozen in time, right? Let's say you're walking and you fall over and you die in the stream and then everyone covers you with dirt. But they didn't know how to bury you. You ate them or you didn't, right? Anyone who didn't get ate became a fossil in some cases. Some of them rotted. Okay. Metamorphic rock. I don't think we're going to talk about that in the context of Mercury or the moon, but we certainly will see it when we get into some of the other terrestrial geology. Of course, for the rest of the planets that are not the terrestrial planets, there's no geology at all, right? It's all atmosphere. Okay. Let's look at how many things did I do here? Oh, right. Okay, hold on. I forgot what I was doing. Oh boy, this is when you don't have coffee anymore. All right, hundreds of minerals have been identified in minerals. There are thousands in earth rocks, and this really has to do with difference in chemistry. It has to do with the difference in the availability of certain elements. We talked about this, right? Silicates are using this tetrahedyl SiO4, right? And they are abundant because silicon and oxygen are abundant, right? And it's easy to build stuff. Like nature is not like how do I say this properly? Nature is not like a cool designer who tries to use like edgy materials to look very cool. It's like, what is available? Good. What builds stuff good? Good, right? Like that's why the things are what they are. When you look at the composition of humans, we're made from carbon, nitrogen, oxygen. Why? Because carbon, nitrogen, and oxygen are available. Right? That's the easiest way to think about it. And I'll show you this when we look at schnapps in a few seconds. Similarly to the CO4 unit is the carbonates, right? So silicates and carbonates, this is just, instead of Si, you're using C, right? But you have this carbon, so silicon doesn't form silicon dioxide, for example. Whereas if you have free carbon and you have any oxygen lying around, it has no problem forming carbon monoxide, which is CO, stuff that makes you sick, and CO2, which is probably the original atmospheric constituent. So C is probably less available than silicon when you look at the elemental abundance that we're about to do. So let's have a look at that. Right, here's the abundances of the elements in the sun. And remember, we did this. Maybe I should have put this like way earlier, but I fixed it now. Okay, so here's our beautiful periodic table, and this one is this one. Hydrogen. That's this one. Helium. Good. What's this one? Cesium. Very good. What's this one? Krypton. Okay, everyone's awake now. Let's go, big B. All right, what does this mean? This row. Yeah, what does it mean? one valence electron. Remember? And so we were looking, for example, at this group, the rubidium strontium, right? And maybe you're doing that on your homework, right? Okay, and then you have this one here. You have the potassium and calcium, and these are the ones that you sub out for, right? You have some mineral concentration. Okay, so now let's think about how this is distributed in the sun. So we look at the distribution of these elements in the sun, and the most abundant thing is hydrogen. Good. Boom. Very abundant. And why did we say helios and helium sound the same? Found in the sun, right? That's where we discovered helium. They're like, oh shit, this really abundant thing is right on the sun. It's like 30%. Right? And then you get to this layer, Li and Be. That's not abundant. That's not present at all. We can talk about that if you care, but you shouldn't care. And then this one too, boron makes cool fires. If you ever burn boron, it burns really fun. But it's not very abundant. And then all of a sudden you jump back up. And you see this seesaw? Yeah. See that seesaw effect? That's a 2. Okay. So you have these first 3, C and O. Carbon, nitrogen, oxygen. What are we made of? Carbon. Okay, good. Can we be made of hydrogen? Yeah, we better be. I'm drinking hydrogen right now. Right? Hydrogen is my favorite thing to drink. What about He? No, that's what this is chemistry. It says chemistry on how no molecules form of He. So the first thing is everywhere. It's in ethane, it's in your farts, right? Okay, these 3 is what we're made of. CNO. And then what? What's this one? Fluorine. CNO. Nope, not made of fluorine. It's not available. Okay, next one? No. Neon. Ooh. Doesn't participate in chemistry. So that one gets passed. Then it goes back down again. So, yeah. So is vitamin D sodium?
Yes.
A little bit. It's a trace element. Magnesium? Yes. We use it in your bones, right? Much more abundant. Right? Okay. And so you can just see how this process works. It's aluminum, that's obviously abundant, but it's not abundant in you. Right? We use it to make stuff, we have to mine it. Whereas like silicon, it's in all the rocks. You don't have to mine it. Right? Okay. We just didn't know how to use it until like 150 years ago. Okay. So now let's look at the Earth. Okay, so this is the most important components of minerals. And you can see, of course, that they line up. We talked about these 2 up here, but they line up pretty well with just what's available. And the reason that we don't use some of the ones that are more abundant, right? You can't use. You can use hydrogen. It's fine. Hydrogen minerals, whatever. But the building blocks here are your oxygen, sodium, magnesium, silicon, aluminum, not fluorine because it's not abundant, not neon because it doesn't participate in chemistry, not carbon because it's being used in the air. And similarly, nitrogen gets fixed, right? So it doesn't necessarily participate in the same chemistry. These stones, they're just like sitting around and they're like, oh, let's make rocks out of here. Okay. Iron, love some iron. Love me some iron in my rock, right? Well, what's an iron rich rock? Oh. What's an iron rich rock? Okay. And what would we call those? It's like a group of these rocks, right? You remember? Right? What does methane mean?
Iron and something rich.
What does the M in methane mean?
Magnesium.
Magnesium and yeah, what's the thick? What's the word for iron rich? Close, so close. Felsen. Yeah, ferric would certainly be that if it was not in rock. Okay. All right, that was good. Now we're learning some words. And we're almost close to being close to a geologist. Okay. All right, so here's the Mercury. And this is not the Mercury you drink. Yeah, have a good time. Okay, that was good enough. Right?
Yeah, it was okay.
So we'll talk about some of the properties of Mercury. But really what we want to know mostly is comparisons of Mercury and the moon. We'll talk about water on both of these. We won't really talk too much about how Mercury formed because there are some major questions that are still unanswered. But what we'll try to do is, I don't know if we'll do this. I'm really debating this right now. I don't think we'll get this far out of seat today. I'm debating throwing this and tidal locking into this section where we start talking about, say, Jupiter's moons. So I wrote this up here, but it may end up not being covered. Right? So don't necessarily read it. Because the next thing that we want to do is we just want to do comparative planetary geology first, and then we jump into, say, like atmospheres and understanding the giant planets, thinking about them in terms of like what are their giant processes, and then we'll do more geology. We'll do ice geology. We'll do like rings, and by the time we're doing rings, then you really need to know planetary dynamics, and so it's better to do all of those gravitational dynamics at the same time. Because then your brain's just thinking, okay, gravity, right? Right now we're thinking like, ooh, pretty picture, hot, cold, rock, you know? Okay. Oh, by the way, that's the two of them. Right hand side, that's the moon. Left hand side, that's Mercury. What do you notice? Craters, very good, perfect. 10 points for Dante. What else? No mark, right? Okay, so what does that mean? You're almost there. You got it.
There was no mantle that came up to the surface.
Right. Right. Okay. Anything else? This is a small note. I don't know if it's there. There's so many little craters, right? Yeah, this guy's banged up.
But it's also because the way that the moon's facing the earth, so like directional wise, it's why it's on one side, like,
Well, why there's so much marine?
yeah.
Yeah, and we'll see full pictures of Mercury in a few seconds. Mercury has one of the coolest impact structures, in my opinion, in the solar system. It has something called Calorus Basin. And it has an antipode, which means that it got punched so hard that the other side of the planet went. Yeah, it's really cool. I don't know if I have it in these slides, but if I don't, it'll be that'll be our Tuesday discussion. Okay, here's Mercury. Mercury is, do you remember any of the numbers for the moon? What was the albedo for the moon? Yeah, interesting. What's the albedo here? Oh shit, what the fuck, guys? Okay, what else we got here? We got some eccentricity. That's weird. Was the moon eccentric? Not super, like 5%. It's like 20%. That's significant eccentricity, right?
That's like, what is it?
Remember, eccentricity is how squished is the circle. And I'll show you a diagram of how squished the circle is. We'll do a comparison between the two. Okay, density here. That's interesting. What's that mean? More iron rich. Okay, so if I were to hand you a rock and I told you it was 5.5 grams per cubic centimeter, what would you say? You said iron rich, but compare it to other things that we know. Heavier than, yeah, silicon, right? Yeah. More iron rich. So that's kind of weird, right? Or no? Anyone weirded out by that? Is it smaller than moon? It's comparable, right? So look at the size here. Remember, this is 5% of the mass of the Earth. Which, by the way, fucking tiny. Mercury gets to be a planet? Get out of here. All right. And then the 38% of the mass. Or sorry, of the radius. Huh. Interesting. These don't mean anything to you yet, but they will. They're going to be really cool. And oh, by the way, hot. Why is that?
It's so close to the sun.
Bingo. Bingo, dingo. All right, so now let's do a comparison. Oh, ooh. Okay. So we went to Mercury. and we're going there. Bepi Colombo is headed there. I'll update that if I remember. What?
Something has got there.
Did it? Oh, there you go. See, I'm always right on top of it. So Mariner 10 did 3 close flybys in the 70s. In the early 70s, they were just throwing money at NASA. Fly here, gotta make sure the Russians don't look cooler than us. To prove that capitalism is the way. And then once we actually got it, they're like, fuck you. So Messenger was in orbit. I think I need to change this. Yeah. Oh, I guess it's there. It's since 11, but then it only took data for a year. So Messenger has a really robust, or had a really robust scientific payload, and it looked at really cool images that I'm going to show you. Topographic information gives you composition and also magnetic field data, of which they detected almost nothing. Right, that's important for different reasons. I'll talk about it. Excuse me, why don't you work? God. There we go. Did that work? Nothing happened. There we go. Okay, so there's the comparison. All right, so this is what we talked about earlier. So Mercury is a little bit more massive, right? Radius, like pretty close, pretty comparable. The density obviously higher. Albedo identical. Strange coincidence. The obliquity to the solar orbit. Now, what does that mean? Obliquity.
Isn't that like the tilt when it revolves around the sun?
Right. Yeah. So it'll be your axial tilt, right? So here, interestingly enough, Mercury is not tilted. Mercury is almost like straight up and down, as opposed to the moon, which is kind of like askew. Okay. Are they tidally locked? I'm going to tell you yes for both of them. Is there a surface magnetic field? Not on the moon, not at all. There's a little tiny one on Mercury. Is there an atmosphere? There's an exosphere on Moon. Stuff that gets liberated from the surface immediately. Have we visited the surface? One we've stood on. Not we. I haven't done. Okay. And then that's the picture of the book. That's the moon in the foreground, and that's Mercury in the background. That little dot. Okay. All right. Let's look at the interiors, right? So we can see that the we can bounce reflectance spectra, so we can use the fact that the sun is illuminating it, and we know what the sun spectrum looks like. And based on the minerals inside of the rocks that the light is bouncing off of, we know that certain minerals will absorb more of this light and less of that. That's called reflectance spectra. So you can see features. So minerals will have features in the visible spectrum and the infrared spectrum, right? And we can tell without even having to touch the surface, what the first few centimeters, sometimes as much as a meter, what that composition is. Okay, and it looks like they're similar in composition. Feldspar and purity. So what was feldspar again? Again? Sludge rich. And what is purity? What is piercing, Gary? It's a what? You're basically looking at something that is, in both cases, the same type of material. Now, why is this potentially unusual? Well, these two things likely formed in very different parts of the disk, right? We expect, if we don't believe in planetary migration, then we expect Mercury to have started very close to the sun. And therefore, the abundance of volatiles was probably lower because the sun is there and is burning away the volatiles. And the moon, very similar composition, very low in volatiles. Right? But we expect one of these to have more volatiles. Which one? The moon, if it formed it, right? And then we know how the moon forms. We're giving a little bit away at the game, right? However, if you look at the mass distribution, it's weird. So have a look here at these diagrams. Here's the moon, we showed that picture, and here's Mercury. Mercury is just 4. Right? What the fuck? That's weird, right? So from the magnetic field, the fact that there's a very small magnetic field, there's probably liquid in the interior of Mercury, making a diamond. It's small. It's a little baby one, but it's there. Right? Okay. We have talked about planetary formation theories, but one thing that we'll need to try to explain is how does this happen compared to how does this happen? Because remember when we talked about the composition of the moon? What was the exterior made of? Anorthosite, and those are your very light minerals. What's at the center? Which are? What's the heavy? There's 2 things that seem to like sink to the middle. Close. Iron and nickel. Very good. So there's an iron nickel mixture probably in there. Okay. Now imagine you build your entire planet with iron nickel. Right? Like that's a sizable part of the interior of the planet. So the question is, was the original composition of that part of the disk only iron nickel? Or did all of the rest of your silicate-rich rocks, I mean, there still are some there, right there, they're in the same, we just talked about anorthosites being on both. Or was the overall distribution different? Right? And if so, why? That make sense? Okay. So we think that Mercury's been tectonically active. Recent volcanoes on Mercury. That's pretty crazy. So I'm going to show you this here at the very bottom. So this is the edge of something called the Caloris Basin. And if I don't have a picture in here, I'll show you it in a second. This is zoomed in. This is supposed to be that part here. So this is the edge of the Caloris Basin. And there's volcanoes. These are volcanoes. They're not impact crater. Right? What's the difference in impact crater versus a volcano? How do we like visually see that? Pretty circular, good, yeah. So you can tell these are circular, and even though these two, one overlaps the other, right? Like, okay, good. What else can we tell about that? Why is this a crater and this is a volcano? Yeah, but this one doesn't really have a lot of ejecta. I mean, you could make explanations with why you don't have ejecta. What does a volcano do that a crater doesn't do? What? Spew, yeah. So volcanoes, for example, go up. They build. Craters go down. So by getting high resolution topography and by measuring, for example, mass concentrations, you can see whether or not this thing just happens to be a crater, like a divot up on a mountain, or if it built that mountain, right? And then there's a caldera in it. That would be where the stuff came out, right? Okay. Oh, that's it? Yeah, I'll definitely have to include some Caloris-based shit. Cool. Let's talk about water on airless solar system bodies. So, the interesting thing, of course, about something being so light and having no atmosphere is that if you take hydrogen, let's say you have one, hydrogen on, you just put it out into space. One of the first things that happens if it's in space, light hits it and it dissociates. The hydrogen breaks off of the water, and then you have OH and you have H. And that's usually what you see in comets. So for example, water gets liberated from the surface of a comet, it forms a big cloud around it, where that material is just moving away, kind of slowly, and then it gets bombarded with light, and then it dissociates. Okay, so you can turn it into H and O very quickly. And so the question is, do we expect there to be any water on the surface of Mercury and the Moon? Right? Maybe we would think, okay, all this stuff's going to escape, and so there's no reason to expect it at all. But we just talked about those two constituents, hydrogen and oxygen, both existing in the sun, right? That's some of the most abundant stuff. And the sun is constantly belching out what's on its interior in the form of the solar wind. So there's about 10 to the minus 14 solar masses per year. That might seem like very little to you, but of course it's very lot when you think about it in terms of a planet. And mostly of it is protons and electrons. So the protons bury themselves into airless bodies. Nothing slows them down. There's no atmosphere. We're protected from the solar wind on Earth because it hits the top of our atmosphere and forms the ionosphere, right? So we can have solar storms, and we notice that plays with, the telecommunication satellites. But of course, we also have a really beneficial thing called the Earth's magnetic field, which serves to take any high energetic particles and funnel them towards the North Pole so we can see beautiful aurora, right? They're not just pounding into the top of the atmosphere. Okay? So let's say you're burying these protons. They're smashing into the surface. Okay? So each proton can then easily just grab an available electron. Okay? And now if there's any O that's hiding nearby, water loves forming. Water is like, oh, that's my favorite form. It will become water, right? That's why it's abundant. Loves forming. Okay. So it's easy to think about a way that you could get the solar wind and start creating water. Okay. So this is probably how we see widespread water on the moon. Okay. What do we mean by that? Okay. We mean that underneath the regolith, remember we talked about the fact that there's like soil, it's not really soil, but underneath the soil, mixed into the soil, is water. Now that's weird, right? Because we just talked about the fact that on the moon, there are not hydrated minerals in the same way that we have on the Earth. So notice there's a difference in the process. There is water present, not in the same abundances, obviously, as Earth, obviously, right? But there's no evidence for hydrating minerals. Is that process making sense now? Okay. So you have here the temperature on the left-hand side, that's the image you saw earlier, and the water concentration from the epoxy. Okay. What do you notice about these two images? Yeah, I agree. Oh no, so, sorry, this H and G?
Yeah.
No, this is just the figure number. More concentrated or the center. Okay. So here, what did I tell you about the temperature? Hot, 380. And that's where the most water is. Paradoxical, right? Because your expectation should be, well, if it was originally water that formed from whatever forming event, whether it created water, whether it collected water from comets and deposited on the surface, then I would expect it to be at the poles. That's not what it shows, right? We have to be cognizant of our prejudices going into this, right? Okay. But we're running out of time. I never get as far as I think. Okay, and this is the second thing I want to talk about. So comets and asteroids, of course, could deliver water. And there's a lot of evidence to suggest that perhaps Earth's water was delivered by potentially long period comets. This is an ongoing topic of debate. But here's the problem. and say you smash it into the surface, you usually don't leave it, right? So it becomes dissociated very quickly. So what we would expect is because the moon and Mercury, I mean, the moon is tilted, it's about 2% like this. Well, that's not very much compared to our 23.5, which has long seasons. So for example, on Mercury, we would expect that there are craters near the top, near the North Pole, that are permanently in shadow. Okay? And so we would think that if water is delivered to Mercury at any point via impact, that it could collect in those cold traps. Because let's say you liberate water in an impact. And now it's going to start bouncing. There is no atmosphere, right? So let's say it needs a couple bounces. If it falls into the crater, it'll freeze. Because it's permanently in shock. So even though the surface on the daylit side is 440 degrees Kelvin, the interior is probably very cold. There's no atmosphere to transmit that heat. The only thing that can transmit that heat is diffusion through the rock itself, and that's not efficient, especially when you have cooling out the top, right? Okay. So here's the thing. We passed over the poles of the moon, and we showed that there are surface ice in polar craters. This is why some people want to go to the moon, and they want to set up a station and mine the moon's water. Because if you can just grab the water from an open crater, easy, right? You don't have to breathe. That's wonderful for a couple reasons. Because one, we can drink it. That's awesome. Drinking moon water would be like the coolest. Two, you can make fuel from it. And that's potentially more important. Yeah. So how? Difficult chemistry. But you need oxygen to make fuel. So oxygen's heavy. Right? If you could make fuels that are, say, O and H3, which is also abundant on the moon, you can produce very cheap fuels. Plus, then you're on the moon, the moon's easy to get off. Right? So if this is like a way stop, this is what some people want to use, for example, to colonize. Well, we're going to talk about that later. Okay, so this would be part of an asterocometary origin, but the amount required is surprisingly large. So there is some ongoing, I should double check if this is still remain controversial. But this is like ongoing work, trying to understand the distribution of water on the moon, why it forms, where it forms, and how it's maintained, right? Because we know that it should. Okay, sorry, I've already gone over. Any questions about this so far? Okay, if you have questions about the homework or anything else, stop on math. I'm sorry that I wasn't here at noon. Maybe. And I'll try and add some more stuff about chloral spacing because it's sick.